Okay, so let's talk about motion, especially constant speed. We're going to look at hypothetical graphs that mirror what you did for a lab with the tractor and the monster truck. This is not just specific to those vehicles, but anything in the universe that moves in a similar fashion. And what do I mean by similar fashion? Well, it has the same shape graph as you have when you plot distance or position as a function of time. Okay, so I have two such hypothetical graphs. I've got some numbers on here where this point corresponds to around 6 seconds. This point corresponds to around 3 or at the end of this one. And then this position is 120, and this position looks like to be roughly 120 as well. Looks like it came a little short. All right, graphs can be very tricky to interpret because there's a number of things going on at once, and you have to take your time with interpretation. Each part is actually fairly simple, straightforward, but if you're not careful, you'll make simple mistakes. So there's two things we can see about each graph. Okay, something is increasing and something is staying the same. And you want to carefully take time to make sure you understand which is which. So what's increasing? Well, something's going from here all the way up to here and vice versa. Okay, so that's pretty straightforward when you look like that. What's increasing? Distance. Okay, and by the way, what's implicit in this, what's increasing with time? Well, what is constant with time here? What is staying the same for every single second that we have a data point for this line or the other line? Okay, well, the fact they're lines is the hint for this, and if you haven't determined it yet, it is the steepness of that line. One line is steeper than the other, but the amount of steepness is constant from beginning to end. It's always the same amount, and that, of course, what we use for steepness is called slope. So that slope is a very, very important parameter for this graph or this situation. I have two plots for two different vehicles. Their shapes are the same, yet the steepnesses are different. So that steepness must indicate something about the vehicle which differentiates it from the other one. Okay, and you're probably anticipating what that is. We want to understand how we can formally get to that. So what does a slope represent? Well, if I were to find a slope of this one line, I would take a change in the y value over the change in x value. But we're not dealing with x and y. What are we really dealing with? Well, the y is the distance, so it's really just a change in distance. And the x value is, of course, change in time. So if the slope is change in y over change in x, in this case, it's nothing more than change in distance over change in time. That's what you're really finding. So anytime you have time in the denominator, that's a rate. So the slope of this graph represents a rate of change. That's what this triangle stands for. Delta is the Greek letter delta. Change in what? Well, whatever the numerator. In position. Okay? And really, what we're talking about specifically here is distance, but in general, it's a position. So you're basically saying how quickly this object is changing where it is. And we have a word for that. All right, it represents the speed. Okay, or we'll differentiate later, velocity. Now, I understand you all have a concept of speed, how fast or slow something is going. But what you may not appreciate is that we can see speed in these graphs by the slope. The steeper the slope, the faster it must be going, and we can give a specific value for that. That's very, very powerful. You measured two basic things, distance and time, and we can get a third more complex measurement from that by taking the slope. That's speed. So for example, our truck. So our truck, I believe, is the black line. So we have a point that's 0, 0, and then we have a point that's right there. So this went 120 meters, and it took about 3 seconds. So the slope of that truck is not 120 divided by 3, but if we divide that out, 40. And we got to keep the units. We divided the y variable by the x variable, so 40 centimeters per second. And those units reflect what the slope stands for, speed. For the tractor, which is the second line, we've gone the same 120, okay, but it's taken 6 seconds. So the change in position is 120. The change in time is 6 seconds. So that's, see if I can do the math, 20 centimeters per second. So we can see that the tractor is moving half the speed as the truck, okay, even though they covered the same distance. That's very, very, very important concept. We'll be hitting upon that a lot. Now, we're going to step back a little bit. There's another way we could represent that, and that's one-dimensional. If the graph above is a two-dimensional representation of the position and time, we can do it one-dimensionally, and that would be doing with drips of paint. So imagine that monster truck at the back end had a little teeny tiny bucket of paint, and it was dripping the paint at equal time intervals. Let's say every 1 second. What would those drips look like? Well, it's not hard to imagine that if the truck is just sitting there, the dots are just going to pile up, and make a big messy splotch. However, if the truck starts moving, and we know it's moving at a constant speed, which means it's covering the same distance for each time interval, or in this case, each paint drip, we've got a dot, and then a dot, and then a dot, and a dot, and they're equally spaced. Pretty straightforward. So the equally spaced one-dimensional dots here is the same thing as a straight line increasing position, two-dimensional. And if we were to look at the tractor in contrast, right, at time 0 it's here, what would we expect about the dots? Well, the rate at which it's changing its position is less, so the dots would be closer together, but still equally spaced. Okay? So we want to be able to go back and forth between one-dimensional representations and two-dimensional representations. You can imagine then, what if the truck were increasing speed at a constant rate? Let's say it was going faster and faster and faster. What would the dots look like? Well, they couldn't be evenly spaced because that shows a constant speed. So how do we show that we're going faster? Well, fast is the rate at which you're changing your position. So if you're going faster, your position is greater each time interval. In other words, our dots get further and further and further apart. So that shows going faster and faster and slowing down. We're not covering as much ground per drip, so they would get closer and closer and closer until we stop moving and we just build up on there. So we should be able to recognize constant speed, increasing speed, decreasing speed. If that's the case, now let's turn that around and put it on a two-dimensional plot. So in each plot, I've got a straight line that indicates what again? That's right, constant speed. So how would I show increasing speed? Okay, so I'm using this line here as a reference. Well, in increasing speed, I cover, so if I go over a certain amount of time interval, let's say I choose this to be my time interval, I'm going to go a certain distance. Let's say I choose that to be my length. Now I'm going to go the same time interval, but now I'm going to cover even greater distances before, like the dots getting further apart, and then greater, same distance, same time, even further distance, same time, even further distance. And if I connect those steps, I get that. Okay, I get a parabola. So if I erase those little green steps, which you might not have the luxury to do, okay, so I've got most of them. That shows an increasing speed. So two things are increasing in this graph here. We have an increasing position. We're going from 0 position up to some non-zero position, but our slope is getting steeper and steeper. And we can see that if I draw a tangent line right there. Actually, let me do that in a different color. Let me redraw my curve. Okay, so if I draw a tangent line right there where it touches at one point, it's not moving. Then here, I draw a tangent line, it's a little steeper, and then if I draw it towards the end, notice that the steepness of those blue tangent lines are getting greater and greater, which tells me the speed is going up. We can use the same logic with decreasing speed. We're covering less distance for each time interval. In other words, the rate at which we're changing position is going down. So I'm not going to do the stair-step thing, but it'll be the same idea. It would look something like this. Okay, it would turn the other way. It would deviate. And if I draw those tangent lines again, okay, at the beginning, it's fairly steep. In the middle, it's a little flatter. And then towards the end, it's very flat. So that tells us we're going slower and slower. Okay, so those three graphs, 1, 2, and the one at the top, you have to be able to interpret. In all three cases, something is increasing. Position. In other words, where you are. But something is staying the same or increasing or decreasing, and that is the rate at which you're changing position. In other words, speed. So those are easy to confuse. So study those and come in with some questions. Now, what if I want to indicate going backwards at a constant speed? Okay, think about that for a second. In your mind, mentally draw a graph, a shape of a graph that shows constant speed but going backwards. Well, constant speed, we want automatically to think of a straight line. Backwards means our position is getting less and less and less, so that means we must have started at some position other than 0, and we ended at some position less than that. So I go something like that. That should be a straight line. That shows constant speed, much like the first graph, but we're getting less. What's going down, decreasing, is our position. All right, lastly, when we have a line, we can make equations from lines. And so what we're going to come up with is our first set of equations describing motion. These are very simple equations, but they're very, very important. So let me resketch the graph we have from up above. We have distance here, I'm going to call it d, and we have time here. So I'm going to use variables rather than words because it's just simpler, and I have a graph that looks like that. Where the slope of that graph, we already mentioned, is the speed, and the symbol we use for speed is a v. Okay? V for velocity or speed. Well, the first equation we can make is we know that the slope is the change in y over change in x. So we can define velocity, right, as displacement or distance divided by time. Okay? Now, there's another way we can write this. We can write the equation of the line, right? Y equals mx plus b. What's our y variable in this graph? What's distance? Equals, what's our slope? Well, that's velocity, multiplied by x, which is time. And b is 0 in this particular case, but that would be our initial position. So I'll put d initial, okay? But usually that's going to be 0, so you don't have to write that in there. So notice if I rearrange this equation right here algebraically, d equals v times t. The third way we can do it is solve for the amount of time it takes to do something. I'll leave it to you to show where that comes from, but time is nothing more than distance divided by velocity. So 3 ways of saying the same thing, but this equation relates to 3 important measures of motion, not just for the truck or tractor, but for everything in the universe. And that's a very, very powerful statement. Okay, so I wanted to finish up with a simple little example. So let's say the monster truck rolled for 9 seconds. How far would it travel in this time? Well, the monster's truck, the information we know about that from the first graph is that its speed was 40 centimeters per second. Okay? So how can we use this? I don't want you doing this in your head. I want you to do this systematically. So I'm going to list the information. So 9 seconds is time. How far is distance? And I know the velocity. So next I write an equation that relates them. Well, the equation that's most straightforward, if I go to the other side, distance is velocity times time. I don't want to put x's in there or anything like that. There's my equation. Now I'm going to substitute in. That equals 40 centimeters per second, putting in units, times 9.0 seconds. And that tells us 360 seconds cancel out centimeters. Okay? Now, I know you could have done it in your head without doing all this stuff, but when things are more complicated, you want to be able to rely on this. Now, we have the power to predict. How much time would it take to go a total distance of 240 centimeters? So I'm looking for t. What do I know? I got distance, and I still have the same velocity, so I can use this equation here, or I can rearrange it and write time is distance divided by velocity. Distance is 240 centimeters divided by 40 centimeters per second. The centimeters the centimeters cancel out. Seconds flips up top, and I get 6.0 seconds. Very straightforward. What would be its speed then? I don't have to do an equation for that. The speed would still be 40 centimeters per second because we know it's moving at a constant speed based on the shape of the graph. Okay, so this is very basic, but it's very, very important you understand all the subtleties of this. We'll do more practice in class and then pick up from here tomorrow.